Hello and welcome back. When we met in class last time, we finished by very quickly writing the equation of state for a gas of non-interacting particles when they're in equilibrium. So remember, the idea is that if you take any system, there can be many different variables, but in particular, we might care about, well, I don't know, pressure, volume, and temperature, something like that. And the system might start out in some more or less random initial condition. Maybe it starts here, or maybe it starts here, or maybe it starts there, or maybe it starts down here. But what we always find is if you wait long enough, that there is some surface. I'm going to draw it like it's a smooth thing, and it is a smooth thing for an ideal gas. And okay, so there's some. So if I'm plotting here, there's three variables. There's some two-dimensional surface, and what happens is the system, which initially started out in some crazy condition, it kind of wanders here, and eventually it settles down and it finds itself someplace on this surface. And once it gets there, it stays there really forever until something were to something else would have to change to affect it. So it wanders to each one of these points on the surface. Okay, so and it might take a long time. In fact, it approximately takes. I mean, you really have to wait. In principle, you just have to wait forever. So it can, but eventually, so it gets really close to this, and you can kind of imagine what happens if you wait forever plus a day. And it would live on this surface. So if you think about this, this is a graph of three variables. So my three variables are pressure, volume, and temperature here. And we are describing some sort of a two-dimensional surface. It may be flat, or usually it's not. It's going to be curved and bent, or if they're phase transitions, it can have cusps and kinks and things. But there is some sort of a surface in this three-dimensional space. And if you think about it, it means that there's some function of pressure, volume, and temperature which equals 0. That's how people usually write it. So there's some constraint. So that you can't have independent pressures, volumes, and temperature. They're always constrained to live in some lower two-dimensional space. And that you can think of that as a constraint imposed on all three. Now, in the case of an ideal gas, we don't usually write it equal to 0. We usually rewrite it as like you would do in chemistry class. So in chemistry, all of you would have seen that for an ideal gas, the pressure times the volume equals nRT. Now that where R is the gas constant, the universal gas constant. T is the temperature. This is an absolute temperature. So let's make a note here. P is an absolute pressure. Not a gauge or vacuum pressure. V is the volume. T is an absolute temperature. So you need to either use Rankine or Kelvin, as we discussed last time. N is the number of moles. And finally, R is the universal gas constant. Okay. And this universal gas constant has the value, I always forget it, 8.314, blah, 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 more digits. And it would be Pascal meter cubed per mole Kelvin. Okay, let's multiply these. So these are the units in metric units. So 8.314, and then you just figure out what it has to have to have the right units. So, okay, so that's what everyone should have seen in chemistry class. PV equals nRT, PivNert, sometimes people say. The important things is these are absolute temperatures and absolute pressures. If you use any other scale, then you have to adjust the units to get the correct value of R0. And this is a constant, so this works for any gas. So if you can make it an ideal gas approximation, it is the same constant all the time. So this is I want to box this in. This is the chemistry way of saying it. For us, we're going to rewrite this in a little bit different way. For us, we're going to say, if we use moles, label with a bar. So we're going to have a lot of expressions which are almost the same, but some will have mass and some will have moles. And so to distinguish that, when we want to write equations in a molar basis, we'll put bars on things. When we want to use a mass basis, we will use the unbarred expression. So we will write the ideal gas law as this: PV equals in R bar T if we are working with moles, or, and where R bar is the universal gas constant. So that's going to be a fixed number, 8 point, oh shoot, I can't remember, 8.314, there you go. 8 pi, 314, and it would be Pascal meters cubed per mole Kelvin. Okay, that's how, this is what we will use for this class. Another way you can write this is P times V equals the mass of the gas, and we still have temperature. We're going to have a new quantity called R. Okay, so, well, all right, there obviously has to be a relationship between them. And to do that, we remind ourselves that the number of moles times the molecular weight, cursive, equals the mass. Therefore, I can say the number of moles is mass divided by the molecular weight, or plugging all that in here, what we learn is it must be, to make these two equations consistent, it must be that R bar divided by the molecular weight of each gas is equal to R. Okay, so on the plus side, the formula involves mass, which is a more, for us or in our problems, this will be a more reasonable way to quantize or quantify the amounts of things. The downside is you are forced to introduce a new constant, and if you look at it, R bar is the same for every gas, but R would then differ for each gas, and you'd have to look it up or calculate it for each gas. So this is different for each gas. Okay, so R bar, the chemistry number, is the same for all gases. If we want to use a mass basis, the price we pay is that R changes for different gases. Now, it's not that bad because, at least for this semester, we will mostly have, we will have one substance at a time. And so you calculate this number once in a problem, and then it stays the same throughout. So it's not that bad. But it is just one extra little wrinkle that you have. While we're on the subject, there's yet another way you can write the sorry, I lost my whiteboard. There we go. There's yet another way you can write the ideal gas law. And the idea is, instead of using the number of moles, instead use the number of particles. So you could say that is the number of particles divided by Avogadro's number. All right. So in that case, when I write PV equals N R bar T, I use this, I can write that as N over Avogadro's number times R bar T, or rewrite this as number of particles times, and I again will introduce a new constant. It's called the Boltzmann constant, Kb times T, where Kb is the Boltzmann constant, and it has a value of, well, you can kind of see here, it's R bar divided by Avogadro's number. So it's going to be a tiny, tiny number, 1.38, and you can go through the units of it all, but it amounts to 1.38 times 10 to the negative 23 joules per Kelvin. Okay. Now, so to a physicist, this is the natural way to write things, because the natural way of counting amounts is just the number of particles that can interact. In engineering, it will be natural to talk about things in terms of mass, how many pounds or how many kilograms of fuel go into an engine or something like that. So we will use mass basis for engineering problems. And if there's a chemistry kind of problem, the information is given in moles. And they're all equal. You just have to know how to go back and forth. Okay, so those are the different ways we will write the ideal gas law in extensive form. So let's kind of go back. Let's keep on going. So maybe I'll summarize those. So I have PV equals N R bar T, PV equals M R T, and PV equals in KBT. And these are all equal. You just go through use the definitions of moles and molecular weight and Avogadro's number to go between them. Now, I want to highlight something here. On both sides of these equations, there is a variable which is extensive. Namely, they grow with the system size. So, and as I indicated last time, we oftentimes want to have a way to write things which are intensive so that they don't scale. So the equations look the same no matter if you're looking at a large system or a small system. So to do that, what we will do, and we're going to just, well, okay, we'll do it in two different ways. What we will do is divide both sides by an extensive quantity. So for example, and mostly for us, what we want is, so for intensive, for the engineering problems, what we will do is divide both sides by mass. And we will write this as P times the volume over the mass equals RT. And if you think about it, that simply gives P specific volume equals RT, because specific volume is simply the total volume divided by mass, or it's the inverse of the density, right? So over here, we have temperature, that's intensive. We have a specific volume and pressure on the left-hand side. Those are both intensive. In the chemistry case, you can do something quite similar. In the chemistry case, you can write PV. Now the chemist isn't going to divide by the mass, they're going to divide by the number of moles. Oh, sorry. And that will equal R bar T. Now, I can never remember what this is called. Either this is molality, molarity, but it's basically some sort of a, sorry, the inverse of it would be molality or molarity. But something like a volume occupied by the number of moles. I can't remember what the chem vocab is for that. But anyway, I can tell you how it is written. What we would do is think of this as a specific, well, volume over moles. This would be a molar specific volume. This would be specific volume in a molar basis rather than a mass basis. So we would write this as P V bar equals R bar T. So you can see the formulas will look kind of similar in a mass basis and in a molar basis, but the numerical constants are different by an according factor of the molecular weight, and consequently you have to adjust what you mean by specific volume to be, instead of mass or volume per kilogram, it needs to be volume per mole. All right, we won't use this very much, but you will see it in the book, and it's not like it's hard to figure out. It's just a matter of converting the little factors of this and that. This one we will use a lot, and this one we will use a lot. In some of my derivations and motivations, I will use this in class. It won't be used for very many problems. All right, so that kind of ends my lightning review of the ideal gas law. There are a number of practice problems in the homework involving ideal gas law, and I'll go ahead and tell you that I guess the trick, if there is such a thing, is to make sure you always use absolute pressure and absolute temperature. Where people get sideways is, well, one, they will use the constant that's in Pascal and then try to type in pressures which are in atmospheres. That won't work. And then the other thing that goes wrong is that maybe the temperature will be given in Fahrenheit or Celsius, and people will try to use it in the formula, and you always have to first convert it to either Kelvin or Rankine. So those are my two little hints for using these formulas. Okay. In the next videos, I'm going to give, well, there'll be a couple videos which are sort of a crash course in probability and statistics. And then what I really want to do next is motivate the ideal gas law from Newton's laws and concepts of statistics. So the next couple of videos are not material, it's not really material that you're going to be tested on, except for kind of more at a qualitative level, just kind of knowing where things come from. But one of the nice benefits of working through it is it kind of gives you an idea of what temperature actually is, at least for a gas. So that's kind of the big payoff. So the next few lectures are going to be of a little different character. So if they're tough or you're confused, don't worry, ask questions when we meet, and they're a little bit out of the line of the main thrust of this course, but I think it's not too much. And they also, understanding those ideas, help set up the discussion of entropy later in the semester. So, catch you next time.